Okay, we're back. We just did the glass board. Whether we're recording this before we do the glass board, you may never know. But maybe we did, maybe we didn't. So we found that... So what do we find, Blythe, for this? You remember? So again, this is the current. This is supposed to be the current through R2 when you flip the switch to the left so that the battery is connected.
Right. So if we have this expression V equals IR, I equals V over R, and we found that our voltage here is going to be V battery minus V cap over the resistance in the resistor that's in this circuit, which is here, R2.
That's right. So it's the potential difference. The current through this resistor is equal to the potential difference across this resistor divided by the resistance. And so if the capacitor wasn't here, it would just be the voltage of the battery divided by R2 would be the current, right? But the capacitor is here, and it's kind of working against the battery in some ways. And so it's this voltage minus that voltage that that matters for how much current is going to be through this resistor. So let's go ahead and hit play and see what it does.
Okay. Just make sure I use the... Oh. I forgot a T on my VBAT.
Good catch.
Alright. Oh, nowhere to go.
Let me just go ahead and start it over again.
Start the whole thing?
Just hit play.
Oh, okay.
But make sure they can see the graph.
Yeah. So you connect it?
Okay. Well, that was a little different.
Yeah.
And then disconnect it just for fun. See. Okay. So that part still works. So what's different now?
So one thing is that we have now, instead of an instantaneous charge on the capacitor, we have it kind of ramp up in this more gradual way.
Yeah, the resistor kind of slows down the charging of this thing. And so you can see it's a bit more gradual. Maybe stop the program and start it over again just to kind of see that part. So initially, the current is some value, and then it gets less and less and less, and then initially the charge in the capacitor is 0, and it increases to some value. And then once the capacitor is all charged up and good, then you can flip it to the other thing, and it still works like before. So again, the capacitor, once it's charged up, it has some energy. It sort of acts like a battery. The main difference is that the voltage on this battery is decreasing with time because it's discharging. A regular battery, the voltage doesn't change too much, right? So so it works. So we got that part. Nice job. Then we both have colds, I think. So. Gonna make me cough. So the next thing is to kind of play around with some of the values here. So what I want to know is, how does the resistance and the capacitance, the values that we have, how does that affect how long it takes to both to charge up and to discharge? But let's focus on the discharge for a little bit. So do you think that if we increase the resistance, that what do you think will happen?
Well, increase the resistance of which resistor?
Let's try for R1. What happens if you increase the resistance of R1?
think it will.
So it's going to make it harder for the charges to move through, right? So it's going to make it harder for electrons to move through. So it might discharge more slowly. Okay. So maybe let's try that. Let's see what it does. Again, we're only going to be able to see an effect here when we flip the switch back to R1. So it's at 5. What do you want to change it to?
10? 8?
It's up to you.
Trying to
10 sounds good to me. Let's see what that does.
big effect.
So it's going to charge up the same. So that's not going to be any different, we think. Okay? What do you think? Does that take longer?
I think so.
Okay. Maybe change it back to 5, see how it compares. I think it took longer last time. That looks like it's a little shorter because right now it's at 5 ohms. Maybe kick it up to 20 ohms and see.
I thought that.
See if we can make it even more obvious.
Connect.
That's taking a long time. Okay, so
definitely noticed that.
Yeah. So the discharge time seems to take longer with the bigger the resistance is. What do you think about the capacitance?
I think if we increase the capacitance, it should also slow down.
I think it should slow. So it should take longer.
Right.
Well, like we just saw. Yeah, I don't know. Let's find out.
Okay.
Let's find out what it does.
So maybe instead of, let's change this back to 5. This is our initial run. Alright, I'll change this to 1.
So that's about 3 times larger, you think? Because it was 0.37, right? What was it originally?
0.375.
0.375. So about a factor of 3 larger, I guess. Let's see what that does.
So connect, disconnect.
Okay.
It also seemed to
Yeah,
take
that
longer
is.
to discharge as well.
Yeah. Maybe make it even bigger just to prove the point.
Yeah. So I changed it to 2.
Wow, it takes a while.
Yeah.
Okay. So if we increase R, it makes it longer. If we increase C, it makes it longer. What if we increase both R and C?
Then it should definitely make it longer.
Okay. Well, let's find out.
Okay. So I'll keep it at 2 and maybe change this back to 20. Alright, let's see here. So connect, disconnect. And the slope is pretty
Yeah, that's taking a very long time. It's still not discharged. So a fun fact about this, as we wait for the charges to deplete from the capacitor, is that have you guys ever heard about when you have wireless routers and you have to turn it off, and you're supposed to wait? Like everybody says, like wait 30 seconds.
Oh, before you turn it back on again.
That's right.
Okay.
Yeah, so at some point your wireless router starts to act weird and it doesn't work anymore, and you're like, oh no, what do I do? The first thing to try is to turn it off, but instead of just turning it off and turning back on again like a laptop, the advice is to turn it off and then sit there for 30 seconds, which is like a test of your patience, I think, in the modern age. Is if you can sit 30 seconds away for a wireless router. But what's going on there is that there's these little capacitors and resistors inside of that router that store the memory of whatever it's doing. And I think what's happening is that when you disconnect it from the wall, which is kind of like disconnecting it from the battery here, you have to wait for those capacitors to deplete themselves. And 30 seconds seems like a weirdly long time to wait, because the signals are getting sent at close to the speed of light, I guess. So it's a weirdly long time to wait. But if you think about these RC circuits, if the decay time is 10 seconds or something like that, then it makes a lot of sense to wait 30 seconds to make sure that all those capacitors are sort of wiped out. None of the information from before that was causing a problem will still be there. So anyway, it's a fun thing. Even with this laptop here, actually. So if you want to unplug, can you unplug the laptop here? So I have this little light here on my Dell laptop. So now it's plugged in. So I don't know if they can see this light. Can you see this light? Do you see the little bright?
I can see it.
You see how there's a bright light there? Go ahead and unplug my laptop cable. Not that one. Not that one.
Oh, right. Okay.
The power cable.
Yes.
All right.
So this one.
Yes. Okay. And then hand me the power cable here. So again, there's no tricks here. This is the laptop power cable, right? You can still see the light. You still see the light?
Yeah.
It's a little bit dimmer there. I don't know if you guys can see that in front of my fingers.
Oh, you're showing it the wrong way up.
But you can see, and now it's basically gone. I'm going to hold it up here. So that's another thing. And the reason is that there are resistors in here and capacitors, and you have to wait a certain amount of time before the energy that it's stored up in there goes away, and it's basically the same thing here. So that was kind of fun. The next part is what we want to do is we want to double check what the charge is on the capacitor after it's been connected to the battery for a long time. So why don't we set the numbers back to what they were? Put my power cable over here.
All right, I think we're good now.
Okay. So, all right, yeah, we're back to the same parameters. So, go ahead and hit play again, and go ahead and connect it. And what we're trying to do is we're trying to figure out what is this charge here, right? So after a long time of it being connected, how much charge is on this capacitor? And so normally this is kind of a tricky question because the current's changing over time, stuff like that. It's hard to tell. But here's the thing. So here's the secret to answering this question. After a long time, what is the charge on this? Sorry, resistors aren't charged, people. They're never charged. Only capacitors get charged up. After a long time, what is the current through this resistor?
0.
0.
The
So
curve goes to 0.
So if the current through this resistor, so you can see it from the plot, right?
Mm-hmm.
So if the current through this resistor is 0, what is the potential drop across this resistor? After a long time when the current is 0.
0.
0. Potential drop is V equals IR, right? So if the potential drop is 0, then what is the voltage across the capacitor after a long time?
The same as the battery.
Same as the battery. Again, not completely obvious because we have this program and the things are changing and all that stuff. We have all these loops that we're doing, but it should be that should be true. And so if the voltage across the capacitor after a long time is the same as the voltage of the battery, how much charge should be on that capacitor after a long time?
We can go back to how capacitance relates to the voltage and the charge.
Right. So So maybe you want to get out the calculator thing. You remember how to get that on my laptop? There we go. So the charge on a capacitor is equal to the capacitance times the voltage. Q equals CV, right? So what's the capacitance?
So we here have 375.375.
And then the voltage of the battery, I can't read it.
10.
10. Okay, so we should get
3.75.
3.75. Okay. Now we checked this before, but when we checked it before, that was before we had made all these changes to put in this extra resistor. You remember that?
That's right, when we printed it to the
That's right.
console.
So let's check at what the console is saying and see what it gives us after a long time. So we'll go ahead and hit play and see what those numbers do.
Alright, so reset here. Now we get zeros. We connect it. And now they're all very close to 3.75.
Alright. Well, that's cool. That didn't have to work.
Right.
Right. And it was kind of fun because you got to see the charge kind of like slowly go up if you're watching closely enough. So that works. And that's nice because whenever you have a sophisticated program, you've got to be able to test it and make sure that it still makes sense to you, even if it's doing something like kind of tricky, like modeling the time-dependent current on these things. Cool. So